Hello and welcome to a video about Case Study 2. Case Study 2 is a part of the testingcomplexsystems.com website. Let's start with a quick table of contents. First, we'll review the case study goals. Next, review farm operation. Then review how to start and run the combined executable. Then explain the dashboard background activities and all the commands of the test platform. We'll definitely spend some time looking at how to manage concurrency. That includes atomic row insertion. We'll be showing code. Along with that, row locks. We'll be showing code there. And finally, how to make the test platform interactive. For goals, we're going to review the operation of a program with the look and feel of a test platform running against a complex system. We're also going to explore how to manage the concurrency involved in that kind of a program. For a complex system, we're going to use a farm. On the farm are two kinds of animals, cows and chickens. On the farm, there are two types of farming, tending and raising. Tending cows produces milk. Tending chickens produces eggs. Raising either type of animal often produces an additional animal. Otherwise, the animal goes to market. The complexity is going to come in that we will have many of the above activities running at the same time. Looking at the GDS directory, we see two files. Let's take a look at the GDS schema file. The schema file defines three tables: a county table, a farm table, and an animal table. The animal table points back to the farm table, and the farm table points back to the county table. We also see a number of unary values defined. This first group takes care of verification. The second group takes care of execution of the test platform. Let's run the code generator to generate Python code for the schema file. We now see the .py file, and we're going to start the executable. It will execute the .py file and then create counties, farms, and animals for the rest of its execution. So now all the counties, farms, and animals have been generated, and I am just holding the screen up. I'm going to release it. And now, at first glance, there is a lot of information on the screen. It's displaying a dashboard that services user commands that are entered via the UI. Note the UI screen is interactive, and we'll show code on how to do this later. Let's start by reviewing the header. At the top, we have the uptime in seconds. We also have a display of background activities, and currently there are none. This is the overall mode of the test platform interactive operation. Let's take a look at the displays. Start with the farm summary display that takes up basically this part of the screen. On it, for each county, we see the farms, the cow and chicken counts, and indications of the amount of milk and eggs produced. There is another display called the animal detail display. We'll bring it up, and what you can see is that we have a single character here for each type of animal in the animal table. C for cows, X for chickens. These letters can be colored, and further down we'll see how they're used. Let's go back to the farm summary table and start going down the list of commands here. 3 commands to dump rows in the 3 tables. Let's dump the farm table. You can see that there are 0 to 8 entries, or 9 entries, and you can see the farms and the pointers references back to the county each farm belongs to. Let's take a look at how we can work with all the data we have been looking at. We're going to start by creating background activities to both tend and raise cows and chickens. The commands here are Tc and Tx to tend cows and chickens, and Rc and Rx to raise cows and chickens. Let's start the first type of activity up, Tc for tend cow. You're asked how many background tend cow activities do we want? The default's 3, so we'll use that. Going up to the header, you can see we now have 3 tend cow background activities running. And then looking through the farm summary table, you can start to see that we are getting milk produced by the cows that are being tended. As it goes on, we can add more activities. Let's look at Tx for tend chicken. Again, default of 3 background tasks. And if we go back to the header, we see a second set of background activities. And we see that the chickens are now being tended. We have both new milk and new eggs. Let's do Rc for raise cow, 3 more background activities. And we're going to start seeing the count of animals here start to move up and down as animals are raised and taken to market. So we have all these background activities running. If we want them to stop, we type in an EB command. And if you take a look at that, up at the header, the background activity counts go down to 0. We can start up again more activities if desired. So the verify operation is important. Everything we've done to date is required by the verify operation, and we need to have one because we need to know if some data goes amiss. To start verification, we need to stop all the background tasks. Next, we need to update the farm production tables. You'll see here we have both new and previously accounted for milk and eggs. And now you can see the new milk and new eggs have been transferred over to the accumulated milk and eggs total for each of the farms. Now we need to compress the animal table. We'll start by displaying it. And you can see that in the table we see a number of colored animals. These are erased animals. They contain information that has been transferred over to the accumulators for each farm, but now the animal rows have to be erased themselves. And after we execute the command, you can see all the cyan animals have disappeared. So we put the farm summary display back, and we go to run the verify all command. We've run the command and then paused the output. You can see that it does indicate in green that the counts that we are concerned about indeed do all match. Now we let the screen update, and you can see the numbers themselves. Animal count milk production, egg production, calculated versus observed. Calculated numbers are kept track of as each background task does its job. Observed are the numbers that we see if we simply go down a row and add up the milk, add up the eggs. The VA command actually does a UP command, the update, and a CA command, the compress, before it runs. It's used further down here. Incrementally running pieces of the functionality can be useful when you're testing new code or looking for a suspected bug. But we also need the ability to run for a long period of time. So here we issue an ST command to start a long-running test, and we get asked to define the makeup of the background tasks that will be run during this test. The default is 3 activities, so we'll take those defaults. Next, we're asked for a total runtime of the test, and we'll leave that at 45 seconds. And now we're asked for a cycle time. The cycle time we're putting in is the default 15 seconds. What that means is that the background activities will run for 15 seconds, then stop, then we'll do a verification, then we'll start up the background activities again. Let's do that here. Up in the header, we can see the test run time back down to 41 seconds. The cycle time left is getting down to, actually it does go below 0. At the end of the cycle, we run a VA process, and I'm holding the screen hostage here to stop it. We've just executed a VA command that double checks the value. That's the count of the animals and the count of the milk and eggs that have been produced. Let me release the display. As it moves on, it's a little hard to keep track of the numbers as they're changing. When the test run completes, we do see these accumulator values, and they do match exactly. Let's run one more long-running test, again with the defaults, which are pretty short. And what we're going to do here is inject an error into the system. This adjusts one of the counts so that when the verification runs, it catches it, stops the test from running, and indicates that the counts above don't match. And you can see the milk production values aren't exactly the same. Let's start by looking at the management of concurrency within the program. The first part of it is that one system level lock is used everywhere in the implementation. We don't have more than one lock going at a time. First, the row status column value gets appended last by all the add a row routines, usually under system lock. The code shows you that the appends go down here, and then row status is appended last. And as a matter of fact, the code generator does not accept a table definition if row status is not last. The second part of atomic row insertion is that the accessors to the table scan the table based on the length of the row status column. Even without a lock, if the column values can occasionally be invalid. If we take a look here, we can see the display animal detail routine goes through the animal table based on the enumeration of the row status column. Because row status is always inserted last, the row is either got that value in it or not, and if not, it will not be, the last row will not be scanned. Row locks are the next component of managing concurrent access to rows in the animal table. The row status column and the single system level lock work together to do the job. We will look at the allocate an animal and the 10 cow routines in further detail. To start, the row status column can take on one of three types of values: the null string or empty string, the non-empty string, and the value of none. The empty string signifies the animal is available for use. The non-empty string means it is in use, and that text can be anything that would be useful to managing, including debug information. Finally, when the animal needs to be erased, row status is given a value of none. So this routine is executed by all the background activities when they want to allocate an animal for their exclusive use. We'll start in the middle by calling the system level lock, unlocking it, picking a random animal. If it's currently not in use, it's allocated by setting the row status value to something. The master lock is released and the while loop exits. Now we go to the 10 cow routine and we see it calling allocate an animal. If the animal ref is not none, it can be none at times, but if it's not none, we request the master system lock again. We work with the variables to cause the animal to produce, in this case, milk. We pause to keep, we unlock, we pause to keep the animal busy artificially, and then we release the row. This overall logic is repeated in the other three routines that handle the other types of animals. That's it for version 1 of this video. Revisions are underway. Comments are always welcome. Thank you for your time.